Welcome everyone to section number 1. Here we're talking about areas and distances, right? So in this video, we're going to try to calculate areas under functions. We're not going to quite get there. We're going to do approximations, really. So really, our objectives here are to estimate the area under a curve using rectangles with heights given by left or right endpoints. And we're going to try to solve for over or under estimates for the area under a curve by, again, using rectangles. So again, the thing is, right, we're going to do approximations because in general this is very difficult. And to emphasize this, I want to show you this example, right? Find the area between f of x and the x-axis, right? This is the area under the curve idea. Really, it's between the function and the x-axis on the interval from 1 to 4, right? So, okay, here's the interval from 1 to 4. And between the function and the x-axis, so maybe down here, and my goal is to figure out this green area right here. Try my best to shade correctly. There we are. So I want to figure out this area. And in our motivational video, we had a relatively nice function, right, that made a nice geometric shape. It made a trapezoid, right, and we could figure out the area of that trapezoid. But in this case, it's not a nice geometric function, right? There's not a nice area formula that I know in order to give me the area under this function. And so for this video, we're going to be approximating the area under the functions because, again, this is a very difficult thing to calculate. And actually in 4.2, right, our second section here in chapter 4, we're going to tackle the actual area under the curve. But that'll be in the following section. So for right now, let's go ahead and approximate the area between f of x and the x-axis on this interval using 3 rectangles of equal width. So the idea here is that I have this interval from 1 to 4, and I'd like to go ahead and break it up into 3 rectangles, right? So I'm going to do 1, 2, 3. You can see each one of those rectangles is going to have a width of 1. So relatively nice widths. Okay, so that's the easy part. The more difficult part is what should the heights of these rectangles be, right? There are lots of options. I could choose maybe this point right here as the height, or I could maybe choose the middle point here as the height, or I could maybe choose this point right here as the height, right? And kind of for each interval you have this choice to be made. And that's kind of why we have different ways to approximate these things with left endpoints or right endpoints. We can do overestimates or underestimates, things like this. So there's actually going to be several different ways to do these approximations depending on what you want. So in this case, I'm going to do a left-hand endpoint, right? So in this case, for my first rectangle, I'm going to choose this left-hand endpoint over here. This is going to be the height of my rectangle. There we go. And for my second rectangle, right, I'm going to choose the left endpoint. And then for my third rectangle, again, I'm going to choose the left endpoint. And you can see maybe if I shade in these areas of the rectangles, again, this is not necessarily equal to the green area, but it's maybe close. It's an approximation, right? So these ones are kind of overestimates. There's too much area. There's too much orange, not enough green. Here, there's too much orange, not enough green. Here, there's too little orange, right? Not enough green, right? The function actually has more area. So maybe kind of when you add them together, again, it's a decent approximation. And so let's go ahead and actually write down the approximation. So, okay, the width of this rectangle is 1 times the height is going to be 3. So that's the area of this first rectangle. The second rectangle has width 1 and it has height 2. Plus the third rectangle has width 1 and it has height maybe 1.5. And so we have 3 plus 2 plus 1.5, and so let's see, I get 6.5. So the area under this curve, or the approximate area under this curve, is around 6.5. But again, there are different ways to do this approximation. You could have done right-hand endpoints, or you could have done maybe midpoints, or you could have done something more complicated. And so I want to formalize this with, kind of, again, it's kind of a relatively complicated mathematical statement here, but I want to actually put down in words the process that we're doing here. All right, so here we are. The goal of this section, right, is to understand how to approximate the areas with rectangles. And so let's suppose that we have a relatively nice function, right? It's continuous, and for right now, we're going to assume that it's positive, right? And we're going to go ahead and break this up into n subintervals. Really, I want you to think of these things, these n subintervals, as the rectangles. This is specifying how many rectangles that we want. So the number of rectangles. Okay, so we have n subintervals or n rectangles, right? So I'm breaking up this AB into so many pieces. So if I'm looking at this picture over here, we have from A to B, and I'm breaking it up into 1, 2, 3, 4, 5, 6, 7, 8 subintervals or 8 rectangles. The big thing about these rectangles is that we want them to have equal width. Right, so equal width is going to be important here. So this is going to be our delta x, however much that width is. So in our example up above here, right, our delta x was 1, right? The width of this, delta x, was equal to 1. And you saw that each one of these terms had a 1 in it, right? The width was delta x in each one of these terms. But if the width was 2 or 3 or whatever, right, you would have 2 or 3 or whatever that width is times the height. Because again, we're doing areas of rectangles here. Okay, and here comes the complicated part. Because for each one of those rectangles, right, we have to figure out a good height to choose. And there are different ways to do that. And so we need to be able to talk about each rectangle kind of specifically. And that's where kind of this notation comes in here. This is really saying the first rectangle. So this point right here, A, is actually the same thing as x sub 0. And then this point right here, kind of where the first rectangle stops, this is x sub 1. And so if you're considering the interval between x sub 0 and x sub 1, right, you're talking about this first rectangle. And then you'll have a second rectangle and a third rectangle and a fourth rectangle. But in this case, right, if you're doing just n rectangles, right, then your last rectangle is going to be x sub n minus 1 to x sub n, right? So this is going to be the nth rectangle, however many you have. And so you choose a point, right, in each one of those rectangles, and you say, I'm going to use that point to be the height. And so in this case, right, we use the left-hand sides, right, but you could have used the right, you could have used the middle point, or whatever you like. So that's what these x sub I stars are. There's some point in each one of these intervals, right? So this is in the ith rectangle, the ith interval, right? And once you've chosen that good height, then again, the area under the curve is going to be approximately equal to the sum of the areas of rectangles, right? So here's the width, here's the height. Here's the width, here's the height, right? So this is for the second rectangle, and you keep on going all the way until the very end. Here's the nth rectangle, the width and the height, and if you add those all together, the claim is the area of those rectangles right here will approximate the area under this curve. All right, so again, that's technically what we're doing here. This is more the, the formalization of stuff. I think as we do more examples, again, this will become clear. I hope that this example right up here was clear, and then kind of technically, if we want to write down exactly the process that we're doing, that's when it becomes complicated, right? Okay, so the last thing here is, right, which x sub I stars should we pick, right? What heights should we use? And the claim is there are 4 natural choices that we're going to talk about in this course. The first one is an upper sum. This is sometimes called an overestimate. So upper sum or overestimate is when these heights, right, these x sub I stars are chosen to be the global maximum on each one of these intervals, so that you're always getting out the biggest thing. Next, a lower sum, or sometimes this is called an underestimate, right? This is when these points are chosen to be the minimums. Or kind of the easiest ones are maybe the left-hand sum. And this is just where you always choose the left endpoint. So that's the one that we did up here. So I could call this a left-hand sum. Or you can also talk about a right-hand sum. And again, that's when you choose these points to be the right endpoint in each interval. All right, so I have one more example for us to really demonstrate the difference between these 4 things, because they are all different. So I have an example here. Consider this nice continuous function g of x. And I've given you some specific values, right? So at 0, g of x is 1, at 0.5, it's 6, at 1, it's 4, so on and so forth. And we're going to assume that kind of all the absolute maximums, minimums for this function are contained in these above points. So I'm not trying to hide anything from you guys. And then the goal is to use 4 rectangles, and I'm going to calculate an upper sum on the interval from 0 to 2, and we're going to calculate out a lower sum and a left-hand sum and a right-hand sum, all these good things on the interval from 0 to 2. Okay, so before we get to actually solving these problems, let me go ahead and I want to draw maybe an example of what g of x could look like. So I'm going to go ahead and draw g of x. So here's 0 to maybe 2, so here's 1, and here's 0.5, here's 1.5, and then, okay, I need to be maybe a little bit more generous with my scale here, so maybe here's 1, 2, 3, 4, 5, 6, something like this. So at 0, we have a height of 1. G of x spits out 1. At 0.5, it spits out 6. At 1, we get 4. At 1.5, we get 2. And then at 2, we get 5. So this is all the information that I know about g of x, but I'm going to go ahead and maybe plot some points between these things, or to just sketch a curve between this to kind of get an idea of maybe what g of x looks like. It's going to be a nice continuous function, something like this. There we go. So that's an idea of what my g of x looks like. And I want to calculate, again, the area under this thing, or the area between this curve and the x-axis on the interval from 0 to 2. And again, this is kind of maybe quite complicated. Has a lot of curvature to it. And so we're going to use approximations, right? We're going to use rectangles to approximate this area right here. Okay, so I'm going to do a lot of jumping back and forth kind of between this graph, which gives us a nice visualization, versus how can we read it just from the table? Because our end game, we'd like to be able to solve problems like this just from the table of data as well. Okay, so part A, using 4 rectangles, find the upper sum of g of x on the interval from 0 to 2. So notice that from 0 to 2, we already have this broken down into 4 rectangles, right? Kind of 1, 2, 3, 4. Or you can call these 4 sub-intervals if you'd like. So again, I'm going to break up this interval on the graph, right? 1, 2, 3, 4 pieces. So I'm going to use 4 rectangles in this case. Now the easier thing to calculate out, right, is the width of each one of these rectangles. So given that we're doing 4 of them, the width of this rectangle is going to be 0.5. So if you'd like to, you can write down that delta x is equal to 0.5. But okay, I'm going to go ahead and actually calculate out this upper sum. So maybe for my first rectangle, the width is 0.5. Sorry, not plus yet. And then I need to multiply that by a height. And in this case, we're doing an upper sum, which just means we're going to choose the biggest, right? So the upper sum is when you choose the global maximum. And so when you look at this graph here, kind of we have choices anywhere from 1 all the way up to 6, right? From 1 until 6, and I'm going to choose the biggest one around, so that is 6. So it's 0.5 times 6. That's going to be the area of my first rectangle, again, if I want an overestimate or an upper sum. Now, if I was just looking at this table, right, I'd say, okay, here's my first rectangle right here. This is my second one. Here's my third one. Here's my fourth one. But for my first rectangle, I have the choices between 1 and 6, right? So these are the heights to choose from. 1 and 6. Remember, g of x is spitting out heights. So 1 versus 6. And again, if you're choosing an upper sum, you're going to choose the bigger of the two. So in this case, 6. Next up, for my second rectangle, let's go ahead and try to read it just from the table here. So again, the width of my second rectangle is going to be 0.5. Again, it's going to be the same for each one. And then the height, I have the choices between 6 and 4. So I'm going to go ahead and choose 6. Likewise, I can go back to the picture here, right? And so on the interval, my second rectangle, right, here's my first, here's my second, here's my third, here's my fourth. On my second rectangle, right, if I want to choose the maximum, right, that's going to be here at 6. So you can actually double choose points, right? We actually chose this value 6 twice. And this is something nice that happens with upper sums. Okay, on my third rectangle, again, the width is going to be 0.5. And now the height on my third rectangle, I have the choices between 4 and 2. So I'm going to go ahead and choose 4 because, again, that's bigger, right? I want the upper sum, the overestimate. So again, here on this third rectangle, right, I have the choice between 4 and 2. Well, I want to choose the bigger one. And now finally, the fourth rectangle, I have a choice between 2 and 5. I'm going to go ahead and choose 5. So this is going to be the width, 0.5 times 5. And so in this case, let's see, we have 3 plus 3 plus 2 plus 2.5. And so we get, let's see, 6, 7, 8, 9, 10. That's going to be 10.5. And let me go ahead and draw in here what we actually found. So again, for my first rectangle, I chose the height of 6. So I calculated out this area. On my second rectangle, I chose 6. So I calculated out this rectangle. And then for my third one, I chose the height of 4. So I calculated out the area of this rectangle. And then for my final rectangle, right, my fourth one, I chose 5. So notice that in this case, it's called an upper sum because the area is bigger, right? The orange area here that I'm shading in right now is larger than that green area. There's always more of it. So this is an overestimate or an upper sum. Okay, so I'd like you to go ahead and pause the video and try B, C, and D, right? So try using rectangles of width 0.5 to find the lower sum. Notice that the wording is just a little bit different here. So it just says rectangles of width. So instead of saying how many rectangles, it's specifying the width of the rectangles. And likewise, it's changed up the notation again here on C and then on D, right? So using delta x equals 0.5, again, this is specifying a width, right? But it's using different terminology. So I want you to be comfortable with all of these things. And likewise, it says using n equals 4. Again, n, we have to remember, this is the number of subintervals or the number of rectangles. So these are 4 different ways of saying the exact same thing. But now the thing that's changing in each one of these, right? We have upper sum, lower sum, left-hand sum, and right-hand sum. So we're going to calculate out all of these. So again, pause the video, try to get as far as you can on this, and then I'll go ahead and spoil the surprise. All right, and here we go, the lower sum, right? So on our first rectangle, again, the width's always going to be 0.5, right? Width of 0.5, but the height we're going to have between 1 and 6. So we're going to choose 1, again, because it's the lower of the two, the smaller of the two, so it's going to be 1. On our second rectangle, we have the choice between 6 and 4. We're going to choose 4. Let me go ahead and maybe start underlining these things. 1, and then we choose 4. On our third rectangle, we're going to choose 2. And on our fourth rectangle, we're going to choose 2 again. And now when we go ahead and calculate it out, we have the underestimate, or the lower sum, is going to be 4.5. Okay. For part C, again, different wording. Now it just specifies delta x equals 0.5, so you have to be happy with this notation and realize that this means the width of the rectangle. So the width of the rectangle is again 0.5, just like it was before, but now we're always choosing the left-hand sum. So whatever the endpoints are, we don't really care about their values, we're always going to choose the one on the left. Okay, so in this case, on our first rectangle, right, we have a choice between 1 and 6, we're going to choose the one on the left. So that means we're going to choose the 1 in this case. On our second rectangle, we have the choices between 6 and 4. We're going to choose the one on the left, right? And it kind of, again, on the graph here, we were going to choose the one on the left, right? So this is our first rectangle, our second rectangle, so on and so forth. So that's why we have a 6 here. And then we get 4 and 2, right, for our third and fourth rectangle. So for our third rectangle, 4. For our fourth rectangle, 2. Because, again, these are the points on the left. For our right-hand sum, the one that's a little bit different here, right-hand sum, we're going to choose 6 first, then 4, then 2, then 5. 6, 4, 2, 5. 6, 4, 2, 5. Again, because these are all the points on the right, right? On our first rectangle, we have the choices between 1 and 6. We're going to choose the one on the right, 6. On our second rectangle, we have 6 or 4. We're going to choose the one on the right. Then on our third rectangle, 4 versus 2, we're going to choose the one on the right. And then finally, on our fourth rectangle, between 2 and 5, we're going to choose the one on the right. So in this case, we have 6, 4, 2, right? We're always choosing the right-hand endpoints. So in this case, if I wanted to draw out maybe another one of these, this is our area approximation in this case. Something that looks like this. And I'll go ahead and shade in with purple. So this would be the area of these 4 rectangles. We add them together. Again, it's going to approximate the area of the green, the area under the curve. But in this case, we were using the right-hand sum, right? Always choosing the right endpoint. Okay, and the big thing that I want you to notice here, I chose this example very specifically because the upper sum, the lower sum, the left-hand sum, and the right-hand sum, they all give different numbers, right? 8.5, 6.5, 4.5, 10.5, they are different. And there's some common misconception that people think upper sum and right-hand sum mean the same thing. No, they don't, right? And likewise, lower sum and left-hand sum do not mean the same thing. They can give different values. And so you do have to be very careful and very specific about which one you're calculating out. Now, one common thing that you will does always hold true is the upper sum is always the largest, right? And the lower sum is always the smallest. So notice 4.5, 10.5, those are the smallest and the biggest respectively, right? The left-hand sum and the right-hand sum, those are somewhere in between, right? They can be equal to it. It can be coincidentally equal, but they don't have to be, right? Okay, that's our final example. That's it for this video. Next time, we're going to talk about a few applications. I'll see you guys then.